You know that feeling when you find a fascinating old document and it feels like you've discovered a time capsule? Well, in the world of science and engineering, papers are kind of our time capsules. But what if we could do more than just read them? What if we could actually bring them back to life? That's exactly what we're going to dive into.
All right, so this is our artifact. It's a circuit diagram from a really foundational engineering paper published all the way back in 1985. It describes a component called a monolithic 3-bit phase shifter, which was designed to work across a huge frequency range. We're talking 6 to 18 gigahertz.
So, what in the world is a phase shifter? Well, in simple terms, it's a supercritical piece of technology that precisely adjusts the timing of a signal. A good analogy is to think of it like a conductor in an orchestra, making sure every part of a complex system, say a radar or a satellite link, is perfectly in sync. It's a fundamental building block for sure. Now, the knowledge in that 1985 paper is incredibly valuable, but there's a catch. It's trapped. It's stuck inside a locked room, just printed on a static page. And this gets right to the heart of the problem. We can all open a PDF and read it, but can you ask it questions? Can you test its assumptions or play around with its data? Not really. The knowledge is presented to you, but it isn't interactive.
And, this creates some real limits. The data from all those charts and tables can't be easily pulled out and reused. It's really hard for other researchers to independently verify the findings. And if you want to build on this work, you're pretty much starting from scratch, manually recreating the models. It's a beautiful snapshot, but it's completely frozen in time.
But what if there was a key to unlock that room? What if we could actually transform the static PDF into a dynamic, living program?
This is the big idea, creating something called an executable companion. It's not just the paper anymore. It's the paper plus a whole set of tools, code, data tables, and documentation that lets you actively explore the science that's inside it.
So how'd they do it? A special pipeline was developed for exactly this. First, an AI model reads and understands the entire 1985 paper. Then, it automatically identifies and extracts all the key technical parameters. From there, it builds a computational model based on the engineering principles in the paper. And finally, it generates everything you need: simulator code, documentation, and even new data based on that model. And we have to give credit where it's due. This impressive transformation pipeline was developed by the company DBbun LLC, and they used Anthropic's Claude AI model as a core part of the process. The entire project is now hosted and available on IEEE DataPort for anyone to check out. Okay, now what's really interesting here is seeing the result of that extraction. I mean, look at this. Information that was once just buried in paragraphs of text is now perfectly organized. You've got minimum frequency, maximum frequency, phase error, chip width. All of it is neatly structured, sourced, and ready for a computer to actually use. This is that first big step to unlocking the knowledge. With the data unlocked, we can now open the door and really bring this nearly 40-year-old paper into the modern world. So let's see what that looks like. And this illustrates the transformation perfectly. On the left, you see the original chart from the paper. It's just a static image. But on the right, you see what's possible now. We're no longer just looking at a picture of the data. We can actually interact with the underlying model, run new simulations, and explore the results for ourselves. For example, we can now easily compare different scenarios. Here, we're looking at the phase error at 6 gigahertz. We can simulate the ideal performance, compare it to the predicted performance described in the paper, and even model the measured results, which had a much higher error. This kind of analysis is now literally just a few clicks away. Now, this is a crucial point, and it's a really important one. The new datasets and code are not the original author's raw experimental data. They are, as the documentation puts it, synthetically generated artifacts that are inspired by the paper. Think of them as powerful new tools for understanding the original work, not as a replacement for it.
So this is way more than just a clever trick for one old paper. It points to a fundamental shift in how we might interact with scientific knowledge in the future.
This comparison really highlights the new paradigm. The old way was all passive consumption. You read a paper. The new way allows for active exploration. We move from just having an abstract understanding of the concepts to a direct computational interaction with them. Information that was static becomes knowledge that is dynamic. I mean, just imagine a future where scientific literature is fully interactive, where you can run simulations right from the document you're reading. A world where you can easily inspect the author's assumptions and reuse their work, not by retyping it, but just by running it. That would accelerate discovery like crazy.
And hey, this isn't just some sci-fi concept. This specific project, this executable companion to the 1985 phase shifter paper, is available right now for you to explore on IEEE DataPort. You can go download the code and the data and see it for yourself.
And that brings us to the final, really powerful idea here. If a complex engineering paper from nearly 4 decades ago can be resurrected in this way, what does that mean for the vast library of human knowledge? It suggests a future where our entire technical heritage could become more accessible, more interactive, and more alive than ever before. It really makes you wonder, what paper would you want to see revived next?